Thanks. So this time I would like to present a second tool. The name is Coming, that also we have developed with Martin Moporeus. That is for mining instances of code changes. Okay. So what is Coming? Coming came from Coming mining. So it has two main users. The first one is to compute fine-grained changes between two consecutive revisions. And the second goal is to mine instances of code change. For instance, I want to get all the commits that introduce an if and a return. Okay? Each commit will be an instance, or will have an instance of this change pattern. And also, one thing that Coming also provides is to compute the frequencies of code changes. Okay? For instance, it returns the number of commits that add, for instance, are return null. Okay? This is the goal. So why we create Coming? So with two goals. The first one was to study software evolution. And the second one was to support our research about automatic software repair that I present during the morning. So, to study the software evolution, we wanted to know how an application evolves during the life cycle. In particular, we wanted to know how developers repair bugs. For instance, the probability of changes. Which are the commits that introduce bug fixes, with which probability are to, for instance, doing some kind of changes, etc. And the second one, so the state of the art about this software evolution, the study of software evolution, was when we started doing Coming, there were one tool that was Equalizer that was basically was a database that store all the changes from a Git repository. It was a relational database, and all the changes were computed with an algorithm, and also was the tool that the name is change distiller. But the problem that we found in that time was that the code change that change distiller provides was too coarse-grained level. For instance, one of the outputs of change distiller was update of method invocation. Imagine that you have this change, and change distiller say, okay, here you have an update of the method invocation. That is right. But actually the change was, it changed the argument, the parameter. So it's too coarse-grained. So actually we wanted to say, okay, here we have an update of the first argument in the method invocation. That this is fine-grained change. So the second part of our research was to supporting our research about automatic software repair. So we need bugs, and we need bugs for repairing, for testing our tools, as Astor, that one that I presented before. So to evaluate automatic software repair tools, we need buggy revisions to apply our repair approaches, and the patcher version. Okay? Why we need the patcher version? Because we need to know which is the patch that the developer have written to repair the bug. Okay? And then with this patcher version, we can compare our results, that means our patches that were automatically generated, with those ones that the developer have created. So the goal is we wanted to mine buggy revision and patch revisions with our tool Coming. For instance, at that time we present an automatic repair system that the name is Nopal. The idea of Nopal was to repair if conditions. Imagine that you have a bug in one condition inside the if, and also to add missing preconditions. Okay? These are the diffs that are able, or the kind of patches that Nopal system are able to repair, to generate. So when we wanted to evaluate no-poll, we wanted to mine real programs, real instances of programs that has this kind of bugs. So we use mining to finding commits that introduce a change inside an if conditions or to add an if precondition. We also wanted that the commit was the commit message, includes some keywords, for instance, a link to a report. And also we wanted to get those commits that introduce, obviously, the if condition change, that means the patch or the precondition, that change the message, and also that introduce a change in the test cases. Why this? Because we wanted to know whether the test cases were updated according when the patch is introduced. Okay? So how coming works? So the inputs are two. One can be the Git repository that we want to mine, okay, to analyze. And optionally, we have another format that is to include one folder with pairs of files. Okay. For instance, one of the files of the pair is the buggy version, and the other is the patch. That means that if you don't have the information to analyze in a Git repository, you can. Common is able to analyze pairs of files. In this talk, I will suppose that we analyze Git commits. So this is the workflow. For each commit, first we apply some filters according, for instance, to the number of file modifier, the number of hanks that each file introduces, the size of the hanks in number of line of codes, the presence of keywords in the commits, etc. So we apply the filters, and then we decide whether we accept the commit or not. If we accept the commit, then we analyze each file that was modified by the commit. Okay, we call it file commit. And then for each file, we generate the AST representation of the modifier file that we call F and the previous version. Okay? So, given a file, we compute the AST. And here we note that there are different ways to create this AST. That means that each node can correspond to different granularities. For instance, the algorithm that I mentioned before, change distiller, use AST that the nodes are very coarse level. That means that, for instance, the invocation, they have all information about the method invocation inside one node. Okay? And another representation of AST, for instance, Eclipse JDT, was two-fan grain level. There were a lot of nodes with not much information. So we decided to work at the level of the meta model of Spoon. Spoon is a tool, it's a library for analyze, transform, write code in Java. This is the meta model. So we wanted to create AST with that level of granularity. Does that mean that given a file, we use Spoon to create an AST where each node is an element from the Spoon meta model. Okay. So the difference is that the Spoon granularity is much finer than the change distiller, but is a bit more coarse level than the JDT that allows us to have more compact AST. So once that we have the two AST, one from the previous version of the file modified by the commit and the file from the commit, we compute the differences. between these two AST. So for computing the differences, so we have the two AST, and we apply an algorithm that compare the two AST and marks the change that the nodes that have been changed, removed, update, or move. We use the algorithm that we have developed, the name is GAM3. GAM3 has two inputs, as input 2, 3, okay? And the output is a list of operations. And each operation is associated to one node, okay? The operations available are insert, remove, update, and move. Okay, once that we have the result given by change distiller, that means the differences between the two AST, we want to know whether these changes has an instance of a code pattern, okay? So, in common we have defined the concept of change pattern. That change pattern define a set of changes between two files, okay? So, a change pattern has one or more pattern action. That means that a pattern action describes one particular change. For instance, one insert, one remove, okay? And one pattern action has the type of actions that are those that came from GAM3, insert, move, remove, update. A pattern entity, that is the description of the code element that is affected by the change. This pattern entity has three properties. One is the type. For instance, the type of the element is a return, an if, and while, an expression, a parameter, etc. The value, okay, for instance, a parameter that the name is my parameter or my method call, etc. Return null. And the parent, that is a reference to another parent entity, okay? For instance, here, with this parent, we can say, okay, I want to detect all the changes, all the method invocations that are inside an if condition, okay? Here, we'll say that the parent allows to express the entity that is affected and the parent. So, Commit provides an option to create this change pattern that is using XML. Here we have a small example of this XML. Here I want to detect, using this pattern, all the changes, all the commits that introduce one if, and inside the if, one return. Okay? So the first part of the XML has one tag that is entity that represents to the return, and the ID of this entity is the ID 1. Then we represent another entity that is ID 2, that is the if. Then we represent the parent. We say that the return has a parent that is the if, and here we relate with the ID. And then we say, okay, I want that one action that is one insert that affects to the entity ID 1, that is the return, and another insert that affects to the ID 2, that is the return. So this way is how we represent a change pattern. So once that we have a change pattern specification in XML, and we have the change between two AST produced by GAM3, we will match both to get the instances. So imagine that we have the previous change specification. Imagine that we have this div, okay, that it adds an if precondition. So the AST changes of this snippet are insert an if in a method body, let's imagine that, and a move operation of the call here, because we change the parent of the method invocation call. So come tree say, okay, there is a move of this method invocation. Here, common is able to match the first action, that means the insert of the if, but we are not able to detect the move, okay, because here the pattern say, okay, I need an insert of a return. So here is a case that there is not a matching. Okay. However, if you have another snipper, for instance here, and add if and inside add the return, here we are able to get from these AST changes, that means one AST changes is the if method, and insert a return. Inside the if, we are able to match these instances. So that means that common will present this snipper, this change, as an instance of this pattern. Okay? Here I present some examples of other specifications. For instance, here we use the value. That means that we want to match a node which value is return null, for instance, or we can match the value of one variable, one method invocation, etc. Here another example with more than 2 entities. We want to match 3 entities that change. Okay? And the output is a JSON file with the revision that has an instance, the name of the pattern, and more information. For instance, where is the instance inside the commit. Okay? How to use commit? So we have the location, in this case the location of the Git project. Okay? Then we specify the mode, the execution mode, here mine instances. There are some arguments for mining a single change pattern. For instance, we can use the argument action to say, okay, I want insert, and the action and the argument entity type to say, okay, the name of the entity type that we want to match. For instance, if, method invocation, return, etc. And here the output, where commit will write the output. Another use, for instance, here I have an example. We say, okay, give me all the commits that has an update of a literal. We don't care about which is the literal that we want to change. We only specify the type. And here we can also specify some filters. For instance, the number of hanks, the max number of provision that we want, the size of the hanks, the max number of files per commit, etc. We have a lot of filters that are documented in our Git space. And finally, another example that we can specify the file of the pattern, the file that contains the pattern that we want to mine. For instance, the pattern that we have seen before. Okay. So the second option is the mode diff that produce as output all it computes a JSON that computes the frequency of the changes. Okay. For instance, it say, okay, here you have binary operator that we found 6 changes that affect 2 binary operators. We have found 2 changes that affect invocation, etc. Commit produce this information at different level of granularities. For instance, here it say, okay, we found 2 instances of invocation, insert of invocations inside the block. We find 2 instances of update of a binary operator inside an if, etc. So they show the information at the different level of granularities. So commit also provides extension points to extend the behavior. In particular, we can specify the input. Right now we have two kinds of inputs, Git repository or file systems. That means pairs of files. We can add new revision filters. With the filters we have right now are related with the commit message, the size of the commit, etc. We can add new analyzers. For instance, another AST algorithm, a new AST with different granularity, a new technique for pattern detections, and we can also add new outputs processor. Right now, the output is present in the standard output or in JSON files, but we can generate another kind of outputs. For the evaluation, so we have analyzed different commits from the dataset default for shape, and we evaluate whether commit was able to detect different instances of change pattern related with if. So most of them were detected. We have two cases of false negatives that actually was related with the output of the AST diff algorithm. Sometimes that happened that the diff produced by GAM3 was too complex, with a lot of changes. And the changes were not as we expect. So that's why we are not able to detect the pattern given such output from GAM3. So to sum up, we found 26 out of 28 pattern instances that all were true positives. And actually, for some cases, Comet was able to find more than one instance of the same pattern inside the same file. So, future work, we are working right now in adding new different inputs and filters, improving the specification that right now is quite simple, but we want to know more features inside, and improving the outputs. It's available on GitHub, so if you want to use it. So we have there the instruction how to extend it, some examples also. So conclusions. Commit is a tool for analyzing fine-grained changes between two revisions. So it allows to mine instances of code changes that were specified in XML languages. It exports the result in JSON formats. The code is publicly available, so we welcome pull requests, comments, etc. Okay, that's all. Thanks a lot.
Any questions? Raise your hand.
Yes.
I have a question because also it's something that also Louis is talking about. So when you're mining the Java file, for example, would you mine the Java code like it is or compile it? And would that make any difference?
So his question was if we mine the source code or the bytecode. So we mine the source code. So we take a version from a commit, we take the source code, and then we mine the changes between the version of the commit and the previous one, but the code source.
Thank you for the level of detail. That was nice.
Thanks.
Did you investigate a solution based on machine learning to generate those patterns, so you don't have to generate like...
Okay. His question was whether if we use some machine learning technique for generating the patterns. It's a nice question. We haven't do that because for the moment we only wanted to get instances for particular patterns. For instance, the patterns that I show add an if precondition or add an if return, because we need it for evaluation of repair approaches. But we can plug, the idea is to plug machine learning techniques to get these patterns automatically. Yes?
Have you heard of other research similar to yours but applied to other languages?
Applied to another languages? No. So I know all the. Yes. So his question was if there is some research related with similar research related with another languages. From my knowledge, I don't know any tool that detects instances of change pattern for another languages. But actually, with Comin, it could be easily done, but changing the AST generator. So that means the parser, you can parse another file in another language, and instead of generating, so we generate the same AST, but using another parser. And then it will be the same. So the matching part will be the same, so it will be similar.
Any other questions? Okay, so thank you very much.
Thanks.